So let's look at suppose the Hessian of a function f is positive semi-definite. Okay, so what does that mean? If it's positive semi-definite, what does that mean? The eigenvalues are all non-negative, right? It's greater than or equal to 0. Then let's look at what is it that you can, let's say x transpose Hessian x. What can you say about this? Can somebody tell me what is the, huh? Huh? Greater than or equal to? Okay, so that's one thing. Anything else? Okay, so now the moment you say greater than or equal to 0, what can you say about x minus y transpose h star x minus y by 2? Definitely greater than or equal to 0. So if I drop this term, what do I get? See, left hand side I'm reducing, right hand side I'm reducing, right, by dropping it. So that means f of x is greater than or equal to, this implies f of x is greater than or equal to f of y plus x minus y transpose gradient of f evaluated at y. Right? You get this inequality, right? Do you agree? Is that clear? Fine? Okay. Okay. Let's look at this is one observation. So suppose the minimum eigenvalue of the Hessian is lambda min. Then of course it is lambda min greater than 0. Okay, so that means it has a non-zero eigenvalues, strictly positive, right? So then what can you say about this thing, x transpose hx? In fact, h is h star also, right? Because it doesn't matter at what point you are evaluating Hessian. This is true for all. The Hessian is the minimum eigenvalue of the Hessian is lambda min greater than 0. This is irrespective of the points that you pick in the domain. You pick any point, it's always greater than lambda min, and it's positive definite. Basically, I'm saying it's positive definite. Then what can you say about this? Okay, I can do this, right? So x transpose hx divided by, I can divide by norm squared. Do you agree? I can multiply and divide by norm squared. Okay. Now I can write this as norm squared times v transpose hv, where v I'm going to write it as x by norm of x. Do you agree? This is simple algebra, right? X by norm of x and x by norm of x, it will be norm x whole squared. I get back this, right? So what can you say about this vector v? V is a unit vector. Okay. So now, what can you say about v transpose hv? So v transpose hv, what can I say about this one? What is the value of, so what is the least possible value that v transpose hv can take? Huh? Why is that? Because I can choose v to be the eigenvector corresponding to the least eigenvalue, right? So you'll get lambda mean. If you choose any other vector, it will have a component in the direction of other eigenvectors, which is larger than lambda mean, right? So you can verify that. So this is greater than or equal to lambda mean. So what do I get here? So this will be greater than or equal to norm of x squared times lambda mean, right? So therefore, this implies x transpose hx is greater than or equal to lambda min times norm of x squared, right? Fine. So then using this, what can you say about f of x?